This chapter is about reaction rates and equilibrium. In section 1, we're going to be talking about rates of the reaction. So in chemistry, there's this thing called the collision theory, and it says that molecules must touch or collide in order to react. Collisions must equal or exceed something called the activation energy, which is the minimum energy needed to start the reaction. So if we look at a potential energy diagram here, we have energy on our y-axis and reaction progress on our x-axis. We have a curve like this. This is called a potential energy diagram. So on the left are always the reactants, the potential energy of the reactants, and on the right are the products. So the difference between the bottom of the graph, 0, and the top of this line here, that represents the potential energy of the reactants. And on the right, we have a similar arrow showing us the potential energy of the products. The difference between the potential energy of the products, this line here, and the potential energy of the reactants, this line here, that is our delta H, you remember from last chapter, the potential energy of the products minus the reactants. The difference in the energy of where we're starting here on our reactants and the top of this curve is called the activation energy. That's how much energy you need to put into these reactants to put them in the higher energy state that is necessary to progress the reaction in the forward direction to produce our lower energy products. If your reactants don't absorb this much energy, the reaction won't happen at all. So a good example of this is paper. So paper is combustible in the presence of oxygen. There's lots of oxygen in any room that the paper is in, but it doesn't light on fire because you don't have enough activation energy to start the reaction. If you put that paper in an oven and turn up the heat slowly, eventually you'll reach the point where the reactants, the paper and the oxygen, have gained enough of this activation energy to get to the tippy top of this hill in order to start the reaction to progress forward towards the production of products, which would be the carbon and the smoke and the carbon dioxide and water vapor. That tippy top of the curve here, where the reactants have gained enough energy, they form something what's called the activated complex. It's a very brief moment in time where these reactants have enough energy and they become very unstable and more likely to progress forward to produce products. So here's an example. I have a reactant here. So this is a compound represented by two different elements here. I have the yellow square and the blue sphere. As they absorb energy, they reach that activation energy. Eventually, they'll go to the tippy top here, where they form that activated complex. Like I said, it's very unstable. The bonds are very unstable, and if they exceed that activation energy just a little bit, they will progress forward in the production of products. So this would be a decomposition reaction where I've produced two separate products from one compound that was once bonded together. So there are four things that can affect the rate of a chemical reaction happening. They are temperature, surface area, concentration, and presence of a catalyst. So if you think of these things in terms of the collision theory, that particles need to collide or touch to start the reaction, these make a lot of sense. So if you increase the temperature, you increase the reaction rate. This is because the particles are moving faster. They have more kinetic energy and they're going to collide with each other more frequently and with more force in order to increase the rate of the reaction. Next, surface area. If you increase surface area, you will also increase the reaction rate, and that is because you'll have more area for collisions to take place. So a good example of this is like a breath mint. If you ever put a breath mint in your mouth and just let it sit there, it takes a while for it to go away. But if you start chewing it into smaller pieces, you've increased the surface area, and the saliva in your mouth comes in contact with the breath mint more frequently, and it will dissolve in your mouth quicker. Next is concentration. Increasing the concentration usually increases the reaction rate because you have more particles of your reactants to collide with one another. It just gets more crowded in your reaction chamber and you'll have more collisions and therefore a faster reaction rate. And the last one is presence of catalyst. So let's talk about what a catalyst is. You may remember this from biology. A catalyst is a substance that speeds up a reaction without being consumed itself in the reaction. So it itself doesn't react, but it helps the reaction happen faster. And it does this by lowering the activation energy. And you may remember from biology, enzymes are proteins that act as catalysts in biological reactions. And life would not be possible without enzymes lowering the activation energies for all of the reactions that keep you alive. There's also an opposite of a catalyst that is an inhibitor. This is something that will interfere with the action of a catalyst. It's kind of just works in reverse. And that's more of a concept for a biology class. We don't usually talk about inhibitors too much in chemistry. So let's look at an endothermic reactions potential energy diagram and how a catalyst can affect it. So we have a curve like this. Remember, there are reactants on the left. The difference between zero energy on the bottom and where our reactants are starting, that is the energy of the reactants. And on the right, we have our energy of the products, the difference between the bottom and the top of this line here. If we look at how much energy we need to absorb to get to the top of this hill in order for this reaction to progress forward, that is called the activation energy. That is abbreviated with an E sub A. So this is the activation energy with no catalyst. Now, if a catalyst is present, what we do is we lower that activation energy from this original curve here to something much lower. This is easier to achieve. So it is more likely to absorb this much energy than it is this much energy. This is like analogous to if you're riding your bike up this hill. It would take longer and it would be harder work for you to pedal up this really tall hill here. But if we took a bulldozer to the hill and lowered it, you would get up the hill quicker and you would progress towards this part faster. So same thing in a reaction. If we lower the activation energy, the reaction happens easier. So the difference between the energy of the reactants where we're starting and the top of this new hill, that is our activation energy with the catalyst. And of course, we can still label delta H here. That's the difference between the potential energy of our products and the potential energy of our reactants here. It's always going to be kind of floating in the middle. Here is the same potential energy diagram, just but with an exothermic reaction. So we are going downhill here. We are releasing energy rather than absorbing energy. The rest of it is still the same. We have our energy of the reactants on the left, the energy of the products on the right, our delta H in the middle, the difference between them, our activation energy without the catalyst, and our lowered activation energy with the catalyst, because of course that's what catalysts do. So let's summarize what we've learned here. So the collision theory basically just says that things need to collide or touch in order to react. Things like temperature, surface area, concentration, presence of a catalyst all affect the rate of a collision, and you need to know how and why they affect the rates of these collisions. Catalysts, of course, speed up reactions, and they do this by lowering the activation energy. If you lower the amount of energy you need to absorb to start the reaction will start quicker, and it will more likely happen than without a catalyst. And also, you should be able to label a potential energy diagram from scratch. So make sure you have those in your notes labeled correctly, and we'll practice a lot of these in class. I'll show you how they ask Regents questions based on them, but it often comes down to just recognizing what parts of those curves go where. So that's it for this video, and if you have any questions, please let me know.